For over a century, Einstein's picture of gravity, as curved spacetime, has been the king. But what if that whole picture is wrong? What if gravity has nothing to do with geometry and is actually more about optics? Today, we're going to dive into a radical new idea that challenges general relativity, and we're going to see how it defends itself against the five biggest questions in all of physics. Okay, let's just frame this right from the start. On one side, you've got Einstein. Mass tells space how to curve, and that curve tells other things how to move. It's a theory of pure geometry. But this challenger we're looking at, it says something totally different. It says mass doesn't bend space at all. Instead, it changes the properties of the vacuum itself, making gravity feel a lot more like light moving through a lens. So this new idea is called gauge theory gravity, and its core claim is that gravity isn't a fundamental force at all. It's an emergent effect, kind of like a side effect. The theory goes that mass, which is really just a bunch of charged particles packed together, saturates the vacuum around it with a potential field. Gravity, then, is just what happens when other objects follow the path of least resistance into a lower energy state within that field. So, let's walk through how this is supposed to work. First, a massive object, like the sun, creates this potential field that just bleeds out into space. This field actually changes the vacuum, turning what we think of as empty space into a kind of physical medium. The bigger the mass, the thicker this medium gets, so when light or another object tries to move through it, it slows down, almost like trying to swim through invisible syrup. Now, look, it's one thing to have a cool-sounding idea, but if you're going to step into the ring with a heavyweight champion like general relativity, you have to do more than that. You have to be able to answer all the hardest questions and explain everything we already know to be true, but from your new point of view. And that brings us to what proponents call the gauntlet. These are the five great challenges, the five biggest, baddest, most fundamental objections that any alternative to Einstein has to overcome. And today, we're going to go through every single one and see how this new theory holds up. And that brings us to challenge number one, the neutrality problem. Right away, this seems like a huge hole in the theory. If gravity comes from the potential fields of charged particles, how come it pulls on things with no charge? A neutron has zero net charge, but if you drop one, it falls. So how on earth does an electromagnetic-based theory explain that? The attack is simple and brutal. Your theory is all about charge, but gravity doesn't care about charge. The defense, though, the defense is fascinating. It doesn't try to dodge the question. It attacks the very premise by making this incredibly bold claim. When you get right down to it, there's no such thing as a truly neutral particle. And here's how they back that up. First off, a neutron isn't just a dot. It's made of smaller things called quarks, and those quarks have charges that just happen to add up to zero. A strong potential field can still grab onto that internal distribution of charges. And second, even if it couldn't, the theory says the potential can just polarize the vacuum around the neutron, creating a little dip in the energy of space itself that the neutron then falls into. Problem solved. Okay, onto the shielding problem. We know how to block electric fields, right? You build a metal box, a Faraday cage, and you're safe inside. But you can't build a gravity-proof box. No matter what you build, gravity gets in. So if gravity is just another kind of potential, why can't we block it? The defense here takes a turn into some of the absolute weirdest parts of quantum mechanics, something called the R-on-off Bohm effect. And what that effect proves is that a potential can exist and affect things even in a place where its force field is zero. The potential is everywhere, even inside the shielded box. So the argument is this: you can't shield yourself from gravity because it's not a force trying to get through your walls from the outside. It's a fundamental property of the space your walls are already in. The potential sets the baseline energy for the whole area. Trying to block it is like being on a boat and trying to shield yourself from the level of the ocean. It's just not possible. All right, time for some math. Any theory of gravity worth its salt has to match one of the oldest laws in the book, the inverse square law. The force of gravity gets weaker with the square of the distance. But the potential in this new theory only drops off as 1 over the distance. So how in the world can it possibly give us the right answer for the force? You'd think this would be a major stumbling block, but it turns out this is actually an easy win. It's not a problem at all. It's a direct result of a really basic mathematical relationship in physics. Force is simply the gradient, or put more simply, the slope of the potential field. And this slide lays it out beautifully. If your potential is a curve that drops off as 1 over the distance r, then the steepness of that curve at any point, which is the force, is mathematically guaranteed to be proportional to 1 over r squared. It's just calculus. The theory doesn't have to try to get the inverse square law. It gets it for free. Okay, next up, let's talk about Galileo and that famous tower. In a vacuum, a hammer and a feather fall at the exact same speed. We call this the equivalence principle. But in electromagnetism, how fast something accelerates depends on its charge-to-mass ratio. So if gravity is an electric-like potential, why don't things with more gravitational charge fall faster?
The defense against this one is maybe the most elegant of them all. It makes this incredible claim. The thing that gravity pulls on, the gravitational charge, is the exact same thing that resists being moved, which is its inertial mass. They aren't just equivalent, they're literally the same thing.
And here's the crucial point. Both an object's inertia and its gravitational charge come from the exact same place, its total energy, the E in E equals mc squared. So, since the force pulling it down scales up in perfect proportion to its own resistance to being moved, the mass just completely cancels out of the equation for every single object. And that is why everything falls at the same rate. The equivalence principle is perfectly preserved. And now we've arrived at the final, and maybe the toughest, challenge of all: time dilation. We know from general relativity that time itself actually runs slower in a strong gravitational field. This isn't just some abstract idea. It's a real effect we have to correct for in our GPS satellites every single day. So how can a theory about a simple potential field explain something as profound as time itself stretching and shrinking? The defense here is just mind-bending. It argues that a strong potential isn't just a force field you're sitting inside of. It is, quite literally, a modification of time itself. The theory taps into this deep, weird connection in physics where electric potential and the flow of time are intrinsically linked. And this illustrates how it works so brilliantly. Deep down, all matter is just a wave, oscillating at a certain frequency. This theory says that a high potential stiffens the vacuum, making those oscillations happen more slowly. And since our best clocks, atomic clocks, measure time by counting those very oscillations, a slower oscillation literally means time itself is running slower. It perfectly mimics Einstein's time dilation, but without ever having to curve space. And this all comes to a head in a famous experiment called the Shapiro delay. Scientists bounced radar off Venus when it was on the far side of the sun, and they found the signal took a little longer to get back. General relativity explains this by saying the sun's mass literally stretched space, so the signal had to travel a longer path. This new theory has a much simpler take. The path didn't get longer, the signal just got slower as it passed through that thick syrup of the sun's gravitational potential. So, in the end, what we have are two completely different models of reality that can both make predictions that perfectly match what we see. One says mass is bending the geometry of the universe itself. The other says mass is just changing the properties of the vacuum. They describe two totally different universes that, from where we're standing, look exactly the same. And that leaves us with this final, provocative thought. Is the universe a passive, disjointed void that things just move through? Or is the vacuum itself an active medium, a connected circuit that fundamentally links every piece of matter to every other piece? This new theory bets on the circuit, and it forces us to ask what the very fabric of our reality is actually made of.